Hey y'all, I'm Miss Keithley. I am back with another video. We're going to be talking about waves. I enjoy this topic so much because I enjoy teaching, honestly. So I'm going to go ahead and begin the video because I don't want it to be super long. I want you to get enough out of it and take great notes so you can use it as a reference. So today's agenda is going to include the vocabulary, the waves, and the sound waves versus light waves. We're going to be comparing and contrasting those two types of waves. So today's agenda, as I said before, we're going to compare and contrast light and sound waves. And we're going to break this video up by kind of talking about the wave types. And we're going to have a great deal of review in this video as well because I know it's going to be kind of detailed. So I want you to make sure that you're able to understand what I'm talking about in the video. So that's why I included a bunch of review within. Also, I included a reminder to grab a piece of paper so you can take great notes. Again, I want you to be able to come back and refer to this. So, vocabulary. I cannot start a topic without telling you some important words that I want you to know. So, vocabulary, we have waves, we have trough, crest, mechanical waves, electromagnetic waves, transverse wave, compressional waves, rarefaction, medium, and vacuum. So what you see right beside compressional wave, you should see longitudinal. And basically, I put those in parentheses because those words can be used interchangeably. So you may see, if you're taking a standardized test, you may see longitudinal or you may see compressional. They're the same thing. So what is a wave? Let's go ahead and jump right into it. If you're thinking about the word wave, it may come to your mind like waves at the beach or waves even when you go to a football game or a baseball game and people are getting up with their arms in the air doing a wave, creating a wave. So, yes, those are all waves and they all have one thing in common. They're just transferring energy, literally. That's all they're doing. So, if you think about it, if you're constantly getting up to do the wave that you see at baseball games with the arms in the air and constantly getting up to sit back down, eventually you get tired because you're basically using that energy to create that wave. And that's all waves do. They use the energies to take it from one place to another. So, as I said, today we're going to focus on sound and light waves. So, the sound waves, those give us the opportunity to be able to hear what we need to hear. And the light waves, they give us the opportunity to see what we need to see. We have two common types of waves, which is mechanical and electromagnetic waves. So we're going to talk about the difference between these two. Mechanical waves, they can only travel through matter. What that means is solids, liquids, and gases. That's matter. So another word I'm going to present to you is medium. That word was on our vocab list. Medium. So medium is another word for matter. So I told you that matter means solids, liquids, and gases. So if you're taking a standardized test or whatever, you may see matter or you may see medium. So mechanical waves, they need a solid, liquid, and gas so they can move through that. Some common examples are the water wave, your earthquake or seismic waves, and your sound waves. Now, electromagnetic waves, they don't have to have a medium. They don't have to have that solid, liquid, or gas. They can move regardless. So they can move through that medium or that matter, or they can move without it. Some common examples are light, radio, microwaves, infrared rays, X-rays. I always tell students you can kind of relate this to real life. When you come in, the first thing you turn on is your electricity, which is the light. So the electro, you hear that electro, basically think of light. So electromagnetic waves, think of those light waves. That's a common type of wave for electromagnetic waves. And also my third bullet says electromagnetic waves are transverse waves. We're going to talk about that right now. So you have two directions that I want to focus on, which are transverse waves and compressional waves. So transverse waves, I want you to think of them like a roller coaster. So those are the ones that's going up and down. The thing that transverse waves include, that compressional waves do not include, are a peak and trough. So your trough, when you think of it, I always think of like the lowest bottom point. It is not the peak at the top, but the lowest bottom point. So that's your trough, and your peak is like the peak of the mountain at the very top, the highest point of the wave. So, transverse waves, I told you they move in the direction of up and down. They include a peak and a trough. The high points in the waves are called crests. The word crest means the exact same thing as the peak. So, the peak of the mountain is the crest of the mountain. The top peak is the top crest. Crest and peak is the same thing. All right, so compressional waves. Another word for compressional wave is longitudinal wave. So if you take a look at this image right here, you see the direction going back and forth. So as I stated before, you may see the word compressional wave or you may see the word longitudinal wave. It is the same thing. The only thing that it's saying to you is that it's going to move back and forth. This type of wave does not include your crest and your troughs. Another word that was on our vocab list that I want to point out to you is that word rarefactions. So, also in this image, you can see that rarefaction basically is that space between those waves. Basically, it's like a reduction of the compression and the compressional waves. So as you can see, it is not so tight right there in that area. It's kind of loose because it includes that reduction of compression. If you know the term compression always means to be tightly packed together. But rarefaction, they're not tightly packed together because it reduces the compression. Okay. All right. So sound waves, as I told you before, everything you hear is due to sound waves. You can hear me clap simply because the sound waves particles are moving. They're vibrating. So even when you talk, the tissues in your throat are going to vibrate in different ways so you can form sounds. That's why people can sing, and you can hear that when they sing because of those particles vibrating. All right, so sound waves are compressional waves. I told you compressional waves move back and forth. So as you take a look at this image, you see those particles. They don't have a peak and a trough. They don't have that. So they're going from left to right. That's the only thing they have, left and right, back and forth. And then they're going to have a medium, which is that solid, liquid, or gas, so they can travel. They have to have that. In which of these three mediums will sound waves travel the quickest? So you can pause this video and you can take a moment to think about that. Okay, you see that I have a red check mark by solid. So if you were thinking solid, that is absolutely correct. Now let me explain why. So let's go back to this image. So on this image, we know we need those particles to move. So we need those particles to move in order so we can hear that sound. We need those to vibrate. But if you take a look at gas, they're not super close to each other. So it's going to take them much longer to produce a sound. We're not saying that they cannot produce a sound. We're just saying it won't be as quick as it is for solid. It may take a little bit more force than solid to produce that sound because they're not arranged properly. But solid, you have them already stacked. Basically, they're ready to go. They're close to each other. They're stacked. So all they need is a vibration to take place and produce that sound. All right, so light waves. I told you when you think of with electromagnetic waves, you always think of light waves because electricity, think of light. So light waves, they do not need to have that solid, liquid, or gas, or that medium, because that's what solid, liquid, and gas means. They can travel through a vacuum. The word vacuum was on your vocab list. Do not think of this word as a vacuum cleaner that you use for your house. We're not talking about that. We're not talking about that. The word vacuum means empty space. I said, do not require a medium and can travel through a vacuum, which is another word for empty space. So, being that they don't need a medium, this is why they can travel so fast. That's because there's nothing basically stopping them from moving. All right. So the question is, why can we see a shooting star, but we cannot hear it? we're going to answer this question once we finish this. So just hang on. So the next slide, we're gonna have this Venn diagram. I kept using the words compare and contrast. And here it is. Basically, we're just wrapping it up for you. So light versus sound, we know in the middle of the circle, it includes both. So light, we know it travels the fastest. It's going to travel in a vacuum. I told you the word vacuum means empty space. So the light waves also help us see. So the light waves help us see. Light waves cannot travel through something opaque. It does not include vibrations. It does not include compressions nor rarefactions. And sound waves, not as fast as light, they can't travel in an empty space or vacuum. They need matter. We know matter is solid, liquid, and gas, and we use the sound waves so we can hear, and they can travel through a solid. And we know that solid is the quickest thing that sound waves are going to travel. All right, let's move on. Please pause this video. If you need to write this down, if you need to write the questions or anything else, if you need to take time out to think about the questions, please do that. So I'm going to move on and we're going to review. So it says a blank wave is a shaped wave known for crests and troughs. So the only wave that you should have been put in this blank should have been transverse, because I told you it's like that roller coaster. It moves up and down. So it's going to have the crest, which is the peak, and it's going to have a trough, which is the bottom point. And then it says a transverse wave can be a mechanical wave, which travels through matter only. So if you have to put M and M together for mechanical and matter, do that. That's M and M. Mechanical needs matter. Or an electromagnetic wave can travel through matter or empty space. Put E and E together. E and E, electromagnetic, empty space. Mechanical waves cannot travel through that. All right, so we're going to answer the last question of today. So it says, why can we see a shooting star but we cannot hear it? We've been talking about this the whole video. So what's in space? Space, right? So of the two types of waves that we've discussed today, what type of wave can travel through space? If you said electromagnetic, you are correct, because I just told you M and M, mechanical needs matter. Mechanical cannot travel through empty spaces. That is only electromagnetic waves. And being that I told you to think of the word electricity when you hear the word electro, so that means this gives us the opportunity to see this shooting star due to the light waves involved, but we cannot hear it because sound waves are a type of mechanical wave, right? Because they move in a compressional direction. That is the answer to that question. Thank you guys so much for tuning in with me, and I will see you guys next time for the next topic.